Alright, so today we're going to look at some list methods, and then we're going to do something interesting with lists, which is going to be implementing Conway's game of life. So let's define a new list. So this list can have both numbers and strings in it. They don't have to be the same types. We can make another one with only numbers in it. You index lists with the square brackets. 0 is the first item, 1 is the second item. If you need to go backwards, just use -1 for the last item and -2 for the second to last item, and so on. We can import the functional library so we can get access to fold left. So we don't have to define our own fold, we just import it. Let's make a small function called times that multiplies two numbers. Then we can use fold left to multiply all the numbers in the list. And if we look at the list and just do this manually, we get the same answer. So you can get the length of a list using the length method or the size method, it doesn't matter which. Push will add something to the end of the list. Then pop will do the opposite, it will take something off of the end of the list. And now our list only has 4 things. We can remove things at a certain index. So let's remove the third item. And we can also insert at a certain index. So we just added the number 15 to the list in the middle of the list. We can reverse the whole list. And we can find elements, and it will give us back the index where they are. Slice will chop off a list at a certain point, so using one argument will slice to the end of the list, but if you want to cut it off before the end, you use 2 arguments to slice. Now let's look at these 2 lists and just concatenate them using plus. Very easy. Alright, sounds good. So let's move on to Conway's game of life. Alright, so before we start implementing Conway's game of life, I have to explain what Conway's game of life is. So it's basically a 0-player game that has this grid of cells. Each cell can be either alive or dead. So here are the basic rules. If an alive cell has 2 or 3 neighbors, it stays alive. If a dead cell has exactly 3 neighbors, it becomes alive. And everything else just becomes dead in the next generation. So from generation to generation, the cells in the grid will change, and you can make some pretty interesting patterns, such as still lifes, which basically stay the same forever, oscillators, which have some periodic repeating pattern over time, and spaceships, which can actually move across the board in a certain way. And you can make some very intricate machinery in the game of life, but for now we're just going to concentrate on 3 really simple patterns. You will notice there's a block still life, which is basically made of 4 squares and doesn't do anything. There is a glider, which moves across the board diagonally, and also a lightweight spaceship, which moves across the board horizontally. And these are the 3 things we're going to see in our example after we finish coding it up. Alright, so let's start programming. First, we need a function that will print the grid. Notice that I have this grid variable, which I initialize to the empty list. Then I push on a bunch of sublists that contain 1s and 0s. So 0 means a dead cell, and 1 means an alive cell. So to print the grid, we need to iterate over all the cells. If it's dead, show a space. If it's alive, show a pound sign. Then we need a new line after every row. That's it for this function. To grab the value of a cell, let's make a function getCell. And I want this to be lenient, which means that if I give it the wrong index, or if it goes out of bounds, I just get a 0. So return 0 if it's out of bounds. We also have to check the row, so let's grab the row. Make sure the coordinate is still within that row. If it's not, then we return a 0 because it's out of bounds. And if everything looks good, we just take the value out of the grid and return that. So for put cell, it's going to be similar, except we're not going to check bounds. Because of the way we're going to design this, checking bounds for put cell is not going to be necessary. So we just make a certain cell alive and that's it. Very simple. And we need to make a new grid for every iteration. So the thing with Conway's Game of Life is that if you try to mutate the current grid, if you try to assign elements into the current grid as you're going over it, it's not going to work. What you actually have to do is keep the old grid in its current state and not change it at all, and generate a new grid on the side, and take the new grid and replace the old grid. If you do it in place, it just doesn't work. It won't have the intended effect. So here we're just making a new grid with a certain width and a height. Everything is filled with zeros, and we return that grid. I'm going to import the functional library so we have an easy way of summing up the numbers inside a list. And now for the Conway function, which will take an old grid and give us back a new grid. So let's get the height and the width of the current grid. So the height is just the number of rows. Then we grab one of the rows, and the width is the width of that row. We just assume that all the rows are the same width, and also that every grid has at least one row. Let's make that grid. Now we need to iterate over the old grid and populate the new grid with the alive cells. So N is going to be short for north. The north cell is going to be the cell above us. So that's going to be J minus 1. J is going to be the vertical coordinate, and I is going to be the horizontal coordinate. So for northeast, it's going to be I plus 1, J minus 1. J minus 1 means go up. I plus 1 means go to the right. So up and to the right is northeast. Northwest is I minus 1, J minus 1. East is just I plus 1. West is I minus 1. So south is the cell below us. So that's going to be J plus 1. Southeast, I minus 1, J plus 1. Oh, no. Sorry. East is I plus 1, J plus 1. Southwest is I minus 1, J plus 1. So let's compute the number of neighbors. All we have to do is add up the list. So fold right of plus, and this will sum up all the numbers in the list. Because each of them is a 1 or 0, we just get the number of neighbors. Okay, so let's get the current cell and check if it's alive or it's dead. So if we are dead and the number of neighbors is exactly 3, then make ourselves alive. Otherwise, if we're already alive and we have 2 or 3 neighbors, keep ourselves alive. Okay, and that should be all we need to do because everything else is already a 0. So I'm going to check to make sure I indented everything correctly, and then we need to return the new grid. So let's do that. So I need a way of clearing the screen. We'll just print a bunch of empty lines, and that should be good enough. Okay, and now to actually run Conway's Game of Life, we need to basically take our initial grid. Well, first we clear the screen, and then we print our initial grid, print the current generation number, and also update that grid with Conway. That should be all we need to run the game. Now we use the input keyword to pause the program at the very end, and that should be good. So the main logic of this program is going to be the Conway function. So it's up here. So basically what we're doing is we're taking all the neighbors, adding them all up, and based on that, we either make ourselves alive or dead. All right, so let's run this program. Okay, so let's run the program and see what we have. So we're going to import conway.cap. And now we can see a lightweight spaceship moving towards the right. Eventually it's going to hit the wall, and when it hits the wall, it's going to degenerate into a glider that's moving towards the upper left. So this will happen soon. Yep, it turns into a glider, and then eventually it stops at the upper wall, becomes a block, and that's it. It's going to stay as a block forever. Wonderful. So in this video, we learned how to implement Conway's Game of Life in Capacita. So thank you so much for watching. I hope to see you in the next video. If you're interested in stuff like this, thank you so much.